FPGA accelerators for lightweight convolutional neural networks, CNNs, have been limited by existing designs. To address these limitations, a novel multi-CE architecture with a balanced dataflow strategy is proposed. This approach minimizes off-chip memory access, thereby enhancing computational efficiency. By incorporating a streaming architecture with hybrid compute engines, CEs, on-chip buffer size requirements are significantly reduced while maintaining low off-chip memory access. A resource-aware memory and parallelism allocation methodology is also introduced, based on a performance model, to achieve better performance and scalability. This methodology optimizes the allocation of resources, ensuring efficient utilization of available computing resources. The proposed accelerator's efficiency is demonstrated on the Xilinx ZC706 platform, using MobileNet v2 and ShuffleNet v2 as benchmark CNN models. The results show a significant reduction of up to 68.3% in on-chip memory size requirements, while achieving a state-of-the-art multiply-accumulate (MAC) efficiency of 94.58%. This is made possible by high DSP utilization, highlighting the accelerator's ability to efficiently process complex computations. This research paper addresses the limitations of existing streaming architectures for lightweight convolutional neural networks, LWCNNs, on field programmable gate arrays, FPGAs. The primary concerns are low computational efficiency, insufficient utilization of available computing resources, and wasted digital signal processing (DSP) units. To overcome these challenges, the authors propose a novel streaming architecture with hybrid computing engines, CEs, which consists of feature map reused CE, FRCE, and weight reused CE, WRCE. FRCE targets optimizing feature map, FM, buffers for shallow layers, while WRCE aims to maximize off-chip weight reuse for deep layers. This approach reduces on-chip memory occupation by 56.67% compared to the state-of-the-art streaming accelerator. Furthermore, a balanced dataflow strategy is designed to improve the computing efficiency of the multi-CE BASED accelerator. This strategy comprises a fine-grained parallel mechanism, FGPM, to enlarge parallel space and a dataflow-oriented line buffer scheme to relieve data congestion. This results in up to a 5.8 times improvement in multiply-accumulate (MAC) efficiency compared to previous single CE-BASED architectures. Additionally, a resource allocation methodology is proposed to explore the design space and leverage limited computing and memory resources on the target platform. This involves adjusting DSP utilization in CE types based on the highly parameterized CE design. The proposed architecture is evaluated with 4 representative LWCNNs and is further implemented on MobileNet v2 and ShuffleNet v2, achieving a high performance of 2092.4 frames per second (FPS) and an almost full load MAC efficiency of 94.58%. The main contributions of this paper include the proposed streaming architecture with hybrid CEs, the balanced dataflow strategy, and the resource-aware memory and parallelism allocation methodology. The background and motivation of LWCNNs with depthwise separable convolution (DSC) and skip connection block (SCB) are also discussed. DSC decomposes a standard convolution layer into a depthwise convolution and a pointwise convolution, reducing model complexity while maintaining acceptable accuracy. SCBs, inspired by ResNet, are deployed for better final accuracy in many representative LWCNNs. The paper provides a detailed analysis of the number of MAC operations and FM memory access cost in different structures, including STC, DSC, and SCB, to reveal the relationship between memory access bandwidth requirements and computing resources. The memory access costs and computational efficiency of lightweight convolutional neural networks, LWCNNs, are discussed, focusing on equations for calculating the number of MACs and FM memory access costs. The disparities between data storage and computational (DSC) and storage and computational (SCB) blocks are highlighted. Ratios of DSC and SCB to standard computational (STC) in terms of MAC operations and FM memory access are computed, emphasizing the need for optimized memory access architectures. The distribution of FMs and weights in LWCNNs is detailed, showing how the number of parameters and weights varies across layers. Efficient memory access is emphasized, along with the limitations of existing designs in supporting LWCNNs effectively. Optimizing memory utilization and computational efficiency for large-weight convolutional neural networks, LWCNNs, is the primary focus of this research. To alleviate the off-chip access burden for feature maps, FMs, a dedicated computing engine, CE, is developed for deep weight calculation, DWC, processing. By fusing this CE with primary weight calculation, PWC, layers, direct FM transfer is enabled without off-chip transmission. However, the DWC CE faces computational workload differences, leading to inefficiency in non-deeply pipelined and spatially tiled DSC structures. To optimize bandwidth in the single-channel buffer SCB structure, an additional buffer is introduced for input data storage and shortcut data transmission elimination. Existing works on multi-CE architectures for LWCNNs are also discussed, highlighting limitations such as low on-chip memory capacity and suboptimal memory footprint. The target of this paper is to reduce both on-chip and off-chip memory utilization while enhancing computational efficiency. To achieve this, a streaming architecture with hybrid CEs is proposed, introducing flexible reconfigurable computing engines, FRCEs, for shallow layers and wide-range computing engines, WRCEs, for deep layers. This design utilizes hybrid data reuse schemes and a balanced dataflow strategy, significantly reducing off-chip memory access and optimizing data congestion, thereby enhancing processing element PE resource efficiency. The paper delves into the optimization of convolutional neural network CNN accelerators, with a focus on minimizing on-chip memory occupation and weight-induced off-chip memory traffic. It categorizes convolutional engine CE layers into two types: feature reused convolutional engine FRCE, and weight reused convolutional engine WRCE, each utilizing distinct data reuse schemes. In FRCE, a fully reused feature map scheme is proposed to eliminate off-chip memory access while minimizing on-chip memory usage. This approach reduces the size of the line buffer and computation delay compared to the line-based reuse scheme. For WRCE, a fully reused weight scheme is introduced to minimize off-chip memory traffic in deep layers. A ping-pong structure-based global feature map buffer is deployed in shortcut connection block (SCB) and pointwise convolution (PWC) layers to store feature map data entirely, allowing each kernel load from external memory to be reused maximally. This optimization significantly enhances the performance of CNN accelerators by reducing memory traffic and improving data reuse efficiency. The research paper presents a technical overview focusing on the comparison between proposed CES, FRCE, and WRCE. Table I highlights their differences in reuse schemes, weight storage, and memory access. FRCE is detailed for its ability to minimize FM buffer size and weight storage, emphasizing shallow layers. The layer-specific CE design is discussed, including the adaptive bandwidth computing engine and its synchronization mechanism. Parallelism across FM and kernels is a key aspect in reducing bandwidth requirements. The process of converting a channel-first dataflow to a location-first dataflow is explained, demonstrating computation and memory usage optimization. The output tile generation and minimizing output buffer size through parallelism in the output channel dimension are also detailed. The proposed memory-optimized architecture eliminates the need for output buffers, reducing on-chip storage resource consumption. The computation procedure for subsequent PF convolution windows is repeated until the entire output feature map, FM, is generated. In terms of WRCE, a similar computation procedure with reversed extended dimensions is employed. A dataflow order converter is introduced to maintain order consistency in the subsequent FM dataflow. This involves decomposing and rearranging input data using multiple banks of RAM with write masks, achieving data order transpose without additional storage space and simplifying data management. The proposed accelerator with balanced dataflow strategy consists of two levels: fine-grained parallel mechanism and data flow-oriented line buffer scheme. The fine-grained parallel mechanism enables large parallel space and efficient computing resource allocation. This is achieved by allocating computing resources proportionally to each convolutional engine, CE, based on the required MAC operations, ensuring balanced dataflow across CEs. Conventional factorized granularity, which reduces design complexity, offers only a small number of integer factors, resulting in unbalanced dataflow and inefficient utilization of processing elements, PEs. In contrast, the proposed fine-grained parallelism mechanism, FGPM, extends the parallel space in each parallel dimension fully, selecting all integer values that can provide different computational times from each dimension as the available parallelism. The FGPM calculates the computing rounds T as T equals ceil, M, P, where M is the maximum parallelism and P is the integer parallelism. This approach enables optimal overall resource allocation, addressing the problem of unbalanced dataflow and inefficient utilization of PEs. The authors of the research paper discuss the advantages of the factor grouping-based parallelism management, FGPM, approach in increasing the parallel space compared to factorization methods. FGPM offers a higher or at least equivalent parallel space, especially for large values of M or sparse factors. By utilizing dimension padding, the size of the parallel space can be increased by 67%, 114%, 175%, 244%, and 340% for common output channel numbers 32, 64, 128, 256, and 512, respectively. This method maintains the regularity of hardware computation and reorganizes excess intermediate results. A comparison between FGPM and previous methods is also presented, demonstrating that FGPM not only conserves processing elements, PEs, for non-bottleneck layers by reducing overall location but also alleviates the staircase effect in bottleneck layers by reducing the parallelism gap. This leads to a relatively uniform and balanced dataflow. Furthermore, the authors address the issue of data congestion caused by inefficient padding implementation and mismatch between buffer organization and convolutional stride. They propose a novel data flow-oriented line buffer scheme, where padding data is not written directly into the line buffer but is instead generated by the address controller within the computation engine, CE, while pixels are sent to the PE array. This approach prevents congestion in upstream data and ensures sufficient bandwidth supply. The paper presents an optimization strategy for streaming neural network accelerators, focusing on resource-aware memory and parallelism allocation. A balanced memory allocation algorithm is proposed to find the optimal trade-off between on-chip and off-chip memory access, based on the analysis of throughput and memory access in the presented architecture. This algorithm involves 2 rounds of iteration to determine the number of FRCEs, or the location of the group boundary, utilizing available on-chip memory to minimize off-chip access and computing latency. Additionally, the paper introduces a dynamic parallelism tuning algorithm to distribute processing elements, PEs, for each layer to achieve maximum throughput with a certain number of digital signal processors, DSPs. This algorithm aims to efficiently allocate parallelism to maximize overall throughput with given computing resources. The theoretical throughput of the proposed accelerator is expressed as a function of the total number of max, computing time, and parallelism of each layer. The proposed methodologies can significantly enhance the performance and efficiency of neural network accelerators, making them more compatible with various deployment scenarios across different FPGA chips and target networks. In this research paper, a novel dynamic parallelism tuning algorithm is introduced to optimize computing resource allocation for bottleneck layers in neural networks. The algorithm iteratively adjusts the degree of parallelism, DSPs, to balance computing time among all computational elements, CEs, achieving maximum throughput and DSP utilization. The proposed multi-CE architecture ensures that each C's execution is regular and independent, allowing for quantitative estimation of overall performance and resource consumption. A resource-aware memory and parallelism allocation algorithm is also developed to explore the design space and enable high scalability, ultimately determining the optimal implementation configuration for a given LWCNN model and FPGA chip. Experiments were conducted using 4 representative LWCNNs as benchmarks for memory and computing simulation. The results demonstrate that the balanced memory allocation algorithm can minimize DRAM access while satisfying SRAM constraints. The proposed design reduces on-chip memory size requirements compared to other streaming architectures, as illustrated in Fig. 12 and Fig. 13. This work showcases the effectiveness and generality of the proposed architecture in optimizing resource utilization and enhancing performance in neural network processing. The evaluation of a streaming architecture for low-precision CNNs, LWCNNs, in terms of on-chip memory size and off-chip memory access is discussed. The authors compare their proposed architecture with baseline and separated CE, SE architectures, demonstrating significant reductions in SRAM footprint and off-chip memory traffic. The flexible group partitioning method, FGPM, is also evaluated for its effectiveness in enhancing theoretical throughput and scalability compared to baseline schemes. The results show improvements in MAC efficiency and better generalization performance across various MAC configurations for 4 benchmark networks. This research paper presents a comprehensive comparison of the efficiency and throughput among 4 lightweight convolutional neural networks, LWCNNs, across a range of MACs. The LWCNNs under investigation are MobileNet V1, MobileNet V2, ShuffleNet V1, and ShuffleNet V2. The results, as shown in Figure 15, indicate that MobileNet V2 and ShuffleNet V2 demonstrate superior performance in terms of MAC efficiency and throughput compared to their counterparts. The paper also explores the optimization of the MobileNet V2 implementation, focusing on alleviating data congestion with a Dataflow-oriented buffer scheme for FRCEs and reallocating computing resources for each layer based on the optimized design. This leads to an improvement in computational efficiency from 69.13% to 84.79% compared to the baseline, with a theoretical efficiency of nearly the same as the current allocation scheme. Furthermore, the FGPM improves both the number of involved PEs and theoretical computational efficiency. Additionally, the authors provide a detailed breakdown of the resource utilization and performance summary for MobileNet V2 and ShuffleNet V2 on the ZC706 platform. The results show high utilization of on-chip computing and memory resources, leading to improved throughput and reduced DRAM access and computation latency. Comparisons with state-of-the-art LWCNN accelerators reveal that the proposed design achieves competitive performance in terms of throughput and computing efficiency. Notably, the MobileNet V2 accelerator outperforms several existing designs but falls short of others with higher DSP counts. However, when compared to a similar design targeting ShuffleNet V2 acceleration, the proposed design achieves a significant throughput improvement. The research presents a novel approach to developing an efficient and scalable low-cost neural network, LWCNN, accelerator. The proposed design incorporates a streaming architecture with hybrid compute elements, CEs, to minimize both on-chip and off-chip memory overhead. A balanced dataflow strategy is employed to optimize computational efficiency by ensuring a balanced workload and sufficient bandwidth for CEs. Furthermore, a resource-aware memory and parallelism allocation methodology is developed to fully utilize available resources while maintaining high hardware efficiency across various target platforms. The results demonstrate the effectiveness of the proposed methods, achieving a state-of-the-art performance of up to 2092.4 fps and a remarkable PE efficiency of up to 94.58%. Unfortunately, it seems that the original text is missing. Please provide the content from the research paper, and I'll be happy to refine it according to the guidelines you specified. I'll transform the text into a concise, technically accurate summary suitable for voiceover narration, maintaining the depth and complexity of the original content.